Bonding in coordination compounds. In order to explain the nature of bonding in coordination compounds, many theories have been put forth, viz. Valence bond theory (VBT), crystal field theory (CFT), ligand field theory (LFT), and molecular orbital theory (MOT). In this module, we shall focus our attention on elementary treatment of the application of VBT and CFT to coordination compounds. Valence bond theory. According to VBT, bonds between metal atom or ion and its ligands is based on coordinate covalency. The metal atom or ion under the influence of ligands can use its N-1d, Ns, Np or Ns, Np, Nd orbitals for hybridization to yield a set of equivalent orbitals of definite geometry. These hybridized orbitals are allowed to overlap with ligand orbitals that can donate electron pairs for bonding. It is easy to apply the valence bond theory to some coordination complexes such as the CO NH3 6 3+ ion. We start with the electron configuration of the transition metal ion. CO3+ Ar 3d6 4s0 4p0. Note that the 4s and 4p orbitals are empty. Concentrating the 3d electrons in the dxy, dxz and dyz orbitals in this subshell gives the following electron configuration. The 3dx2 minus y2 3dz2 4s 4px 4py and 4pz orbitals are then mixed to form a set of empty d2 sp3 orbitals that point toward the corners of an octahedron. Each of these orbitals can accept a pair of non-bonding electrons from a neutral NH3 molecule to form a complex in which the cobalt atom has a filled shell of valence electrons. The complex has octahedral geometry and is diamagnetic because of the absence of unpaired electron. Since the inner d orbital 3d is used in hybridization, the complex CO NH3 6 3+ is called an inner orbital or low spin or spin paired complex. COF6 3- uses outer orbital 4d in hybridization sp3d2. It is thus called outer orbital or high spin or spin-free complex. The complex has octahedral geometry and is paramagnetic. Crystal field theory. Crystal field theory (CFT) describes the breaking of orbital degeneracy in transition metal complexes due to the presence of ligands. CFT considers the metal-ligand bond to be ionic due to electrostatic interactions between the metal ion and the ligand. Consider a molecule with octahedral geometry. Ligands approach the metal ion along the x, y, and z axes. The electrons in the dz2 and dx2 minus y2 orbitals, which lie along these axes, experience greater repulsion. It requires more energy to have an electron in these orbitals than it would to put an electron in one of the other orbitals. This causes a splitting in the energy levels of the d orbitals. This is known as crystal field splitting. The energy separation is denoted by delta O. The subscript O is for octahedral. Thus, the energy of the two Eg orbitals will increase by 3 by 5 delta O, and that of the three T2G will decrease by 2 by 5 delta O. Thus, the degeneracy of the d orbitals has been removed due to ligand electron-metal electron repulsions in the octahedral complex to yield 3 orbitals of lower energy T2G set and 2 orbitals of higher energy Eg set. Some ligands are able to produce strong fields, in which case the splitting will be large, whereas others produce weak fields and consequently result in small splitting of d orbitals. The oxidation state and the strength of the ligands determine splitting. The higher the oxidation state or the stronger the ligand, the larger the splitting. Ligands are classified as strong or weak based on the spectrochemical series. Ligands can be arranged in a series in the order of increasing field strength as given below. I minus less than Br minus less than SCN minus less than Cl minus less than S2 minus less than F minus less than OH minus less than C2O4 2 minus less than H2O less than NCS minus less than EDTA 4 minus less than NH3 less than En less than Cn minus less than CO. Such a series is termed as spectrochemical series. Crystal field splitting in tetrahedral coordination entities. In a tetrahedral complex, there are 4 ligands attached to the central metal. The d orbitals also split into 2 different energy levels. The top 3 consist of the dxy, dxz and dyz orbitals. The bottom 2 consists of the dz2 and dx2 minus y2 orbitals. The reason for this is due to poor orbital overlap between the metal and the ligand orbitals. The orbitals are directed on the axis while the ligands are not. In tetrahedral coordination entity formation, the d orbital splitting is inverted and is smaller as compared to the octahedral field splitting. For the same metal, the same ligands and metal-ligand distances, it can be shown that delta T is equal to 4 by 9 delta O.